And a direct variation is modeled by the formula y equals k times x. The k is the constant of variation, and k cannot be equal to 0 because obviously if k equals 0, then you just have y equals 0 times x, and that is always 0. We say that y varies directly as x, or y is directly proportional to x. So you can hear this discussed in several different ways. To take a look at an example here, we are given the information that during a thunderstorm you see the lightning before you hear the thunder because light travels much faster than the sound. The distance between you and the storm varies directly as the time interval between the lightning and the thunder. So the first part of this question is, suppose that the thunder from a storm 5,400 feet away takes 5 seconds to reach you. Determine the constant of proportionality and write the equation for the variation. In this problem, we're told that the storm is 5,400 feet away, and the lightning gets to us, and then 5 seconds later the thunder gets to us. So what we need to do is find the constant of proportionality. So we use our equation for direct variation, y equals k times x. So we will let the x be the time, and we will let the distance away be our y value, y. So we're going to plug that in. 5,400 equals k times 5. So you can see the process of solving for k is pretty simple. We're just going to take both sides of this equation and divide by 5. And when we do that, we're going to get k equals 1,080. And if you think about the units, that's 1,080 feet per second. And so in the real life situation there, that is the speed that the light is traveling faster than, or that's the speed that the sound travels per second, 1,080 feet per second. So once we know the constant of variation, or the constant of proportionality, depending on what terms you're using, they ask us to write out the equation for this. And so our equation, again, just going back to here, is going to be y equals 1,080 times x. And again, with a problem like this, the variables aren't incredibly important, just so that you know what they're standing for. So in ours, we let the x be the time, we let the y equal distance. I think on the PowerPoint, I actually put a t here for time and a d there for distance. So again, just make sure you understand what your variables are standing for, and that way that won't be an issue for you. But that is our constant of proportionality in our equation. The second part of this question is to sketch the graph of the equation. Then we are asked, what does the constant of proportionality represent? So if we sketch the graph of this b equals 1,080 times t, we'll get a graph that looks something like this. Notice the scales. On the x-axis we have only 0 through 5, and on the y we go quite a bit. And then the question is, what does the constant of proportionality represent? That represents the slope of this line, the 1,080. Part C to this question, if the time interval between the lightning and the thunder is now 8 seconds, how far away is the storm? Now for part C, we're supposed to figure out, using our same equation here for the direct variation, we're supposed to figure out how far away the storm is if the distance between the amount of time between the lightning and the thunder is now 8 seconds. So again, since our time we used as our x value, all we need to do is y equals 1,080 times 8. And so when we multiply that out, we're going to get a 0, and a 4, and a 6, and an 8. So we have 8,640 feet. So it's just a matter of plugging in that value for x, and then we get our answer, 8,640. Another type of variation that we deal with is what is called inverse variation. And the definition of this is that if the quantities x and y are related by this equation, y equals k divided by x, for some constant k, again not equal to 0, we say that y is inversely proportional to x, or that y varies inversely as x. The idea here is that as one of the values goes up, the other one has to go down to make this equation work. Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure of gas is inversely proportional to the volume of the gas. Part A, suppose that the pressure of a sample of air that occupies 0.106 meters cubed at 25 degrees Celsius is 50 kPa. Find the constant of proportionality and write the equation that expresses the inverse proportionality. Okay, in the second example we are given the information that the pressure is inversely proportional to the volume. So we're going to use our equation for inverse proportions, which is y equals k divided by x. We're also given the information that the volume of this gas is 0.106 meters cubed. The temperature is constant at 25 degrees Celsius, and then the pressure is 50, I believe that is kilopascals. So when we set this up, pressure is inversely proportional to volume. We have pressure, and then our constant of proportionality, and then the volume on the bottom. Okay, so our pressure is 50. We have K, and then the V value is 0.106. So to solve for K, we simply multiply both sides by 0.106. And when we do that, that cancels out. We get the K by itself. And then we can just type this into the calculator, 0.106 times 50, and we get 5.3. And once we know that the constant of proportionality is 5.3, we simply go back to here, and to write out our equation for this particular inverse relation, inverse proportionality, we put in the K for, we put in the 5.3 for K, and then we have the V. So our new formula is P equals 5.3 V. Part B, if the sample expands to a volume of 0.3 meters cubed, find the new pressure. To continue this problem, we're told that the volume is now expanding to 0.3 meters cubed, and so that just requires us to put in our new volume, and so that is 5.3 divided by 0.3, and again, that's just calculator work. Type it in, 5.3 divided by 0.3, and we get approximately, and this is rounded off, it's approximately 17.7. Since that's a pressure, that would have the same units as before, so that is kilopascals. So 17.7 is our answer when that, notice when the volume expands, you have the same amount of gas inside, so it makes the pressure decrease. Which would make sense if you think about trying to compress something. It makes the pressure increase. As you give it more space, then the pressure decreases. To do this, all we have to do is plug in the new value for x, and so we have 5.3 divided by 0.3, and that gives us an answer of 17.7. The final type of variation that we want to discuss is joint variation. And this is where we're dealing with more than just two variables. We could be dealing with many variables. But it says if the quantities x, y, and a are related by the equation z equals, sorry, that should be x, y, and z. I don't know why that's an a. X, y, and z are related by the equation z equals k times xy for some constant k, again not equal to 0. We say that z varies jointly as x and y, or that z is jointly proportional to x and y. An example of this one is Newton's law of gravitation, which says that two objects with masses m1 and m2 attract each other with a force F that is jointly proportional to their masses and inversely proportional to the square of the distance r between the objects. We're supposed to express Newton's law of gravitation as an equation. Well, since the force is jointly proportional to the masses, that's m1 and m2, we have that part of the equation being F equals k times m1 and m2. But then, since it's inversely proportional to the square of r, that means, remember the inversely means that that's going to go on the bottom of the denominator. So we have, when we combine these all together, F equals k times m1 and m2 divided by r squared. Some problems that I'm going to want you to take a look at are on section 2.5, pages 196 and 197, 1 through 5, 14, 20, 23, 24, and 26. Again, you'll have time during our next class period to work on those as we're doing this chapter with the flipped classroom, and so you'll have time to ask questions and do your work during class. Enjoy the rest of your evening.